Let me give you some references for studying this quantum Hall effect, and to remind you that we are really talking about the integer quantum Hall effect for now, which can be understood from a non-interacting electronic picture. We don't need to invoke the Coulomb interactions into the problem yet, and we shall be carrying ahead with that. So, I'll give you some references which are important, and they are, this there is a reviews of modern physics, and this is volume number 58, this is volume 58, page 519, and it's a 1986. This is a APS, the American Physical Society, one of the journals on reviews, very famous journal. Then there was another by Robert Laughlin, and this is Physical Review B, and it's a volume 23, page 5632 and 1981. And then there are excellent review article, one of them by S.M. Garvin. This is available in the archive. It's a preprint. It's 99070002. There is another excellent one which I shall be referring every once in a while by David Tong. This is a preprint as well, and it's probably a part of this TIFR Infosys lectures, and this is again available freely in archive 1606. 1606.06687. Apart from that, there are a number of references which may be used. I'll tell you as and when they are used, and they are useful for you to learn the subject. So, let me then go back to the kind of discussions that we have been doing. Let's say the properties of the Landau levels. And to talk about the properties, of course, you know that these Landau levels are absolutely flat. And just to remind you that the energy obtained was like n plus half h cross omega b. It is same as that of harmonic oscillator, excepting that in a usual harmonic oscillator that you learn in the first level quantum mechanics, it is a constant which depends only on the force constant k and the mass of the particle, whereas here omega b depends on the magnetic field. It's actually EB over m, and this is called as the cyclotron frequency. Okay. So, these levels, if you draw them, they look like this is n equal to 0, n equal to 1, n equal to 2, n equal to 3, and so on. And I have argued and showed explicitly that these levels are in principle infinitely degenerate, and the degeneracy is only limited by the value or the magnitude of the magnetic field, and it depends upon the area of the sample. Now, if you take an area to be large enough, They're not very large, but this can be not microscopic but macroscopic area, say a few millimeter by a few millimeter, that is can be called as macroscopic. And then it only depends on the magnetic field, and we have shown that 12 to 15 Tesla of magnetic field is being used. So these are really degenerate, and they are flat, of course. So this is n equal to 0, n equal to 1. Just like a harmonic oscillator, there is no restriction that n equal to 0 won't be available. Remember that particle in a box n equal to 0 was not allowed, because in what it means is that there is no particle there. N equal to 0 means that, but here of course n equal to 0 is an allowed level, and n equal to 3, etc., and so on. Okay, so when I say they are flat, which means that they have no dispersion, so this is E, and they have no dispersion. That means that the velocity of the electrons, if you remember that your band theory, these classes or the band theory chapter, it tells you that Vk is actually 1 by h cross del E del k, or it depends upon the slope of the band energies. Now these are completely flat, so the velocities are 0. Velocity of the electrons are 0, and that means the kinetic energy of the electrons is 0. So the kinetic energy equal to 0. Okay, so they have no kinetic energy, and the only energy that remains is the potential energy. Okay, and because the number is very high, because the degeneracy is very high, it's very likely that they would be interacting at least moderately to strongly, and these effects we'll discuss later when we talk about fractional quantum Hall effect. Okay, but these are some of the properties of these levels. Let's talk about another one. The second one, let's say, is the, of course they are highly degenerate, and which I said, but what are the implications of that? Let us see. So it's the highly degenerate, and it says that we have said this, that the degeneracy is determined by the magnetic field and A, area of the sample. So A is equal to the area of the sample. All right, so this is already known, and now these plateaus that I have shown you several times of the Hall resistivity, so the resistivities have plateaus like this and so on. So these plateaus are, so this is the Hall resistivity. Okay, so let's call it as a rho h, and this is the scale is set by h over e square, and this is n equal to 1. All right, and so this plateaus are actually connected to this degeneracy in the following fashion. So your rho x y or rho h, which is same as rho xy, which is a transverse resistivity, is h over nu e square, where nu equal to 1, 2, 3, and so on. Okay, so now this nu is related to the degeneracy in the following way, that nu is equal to n0 divided by g by a. Okay, where n0 is the electronic density. Sort of going back, that is, I'm revising some of the things that I have already said, and this is nothing but n0 divided by EB over h, and if you remember this, G over A is degeneracy per unit area, and this is I can write this as n0 divided by B and divided by h over E, and that is your h over E in the is nothing but h over E is equal to a flux quantum which has a value 4.13 into 10 to the power minus 15 Weber. All right, so this is the value of the flux quantum. So this is really like n0 divided by b over phi 0, or say n0 phi 0 divided by b. Okay, so this, the integer that you see in the plateaus, that is related to the degeneracy in this particular fashion. Now we demand, or at least the experiments dictate, that nu has values which are integer. So which means that if you really write this as, instead of this, you write this as b over phi 0, then you know, this is actually it'll take integer values when the ratio of the density of carriers and this b by phi 0, and if you do not talk about the degeneracy per unit area, then we can neglect this and can in fact let me remove this degeneracy per unit area and write it as only degeneracy, in which case we'll have a here, which means that these degeneracy is equal to, this is n0 divided by phi upon phi 0. Okay, so then this plateau, integers of the plateau, they actually are ratio of these electron density divided by the flux divided by the flux quantum. Okay, so when this becomes an integer, you see a plateau in the resistivity, and as you change your magnetic field, the phi is changed, then this deviates from being an integer, and then you see that there is a sharp increase in the Hall resistivity, and then till it comes to the next integer, it again then shows plateau in the resistivity. So this is how the degeneracy that we talked about of the Landau levels are connected to the Hall plateaus, or the quantization of the Hall plateaus. Okay, I've already partly answered this question, but number 3, what is the conductivity of the Landau levels? And why I said that I have already or partly answered this question is that I told you that the velocity of the electrons is equal to 0. So if the velocity of the electrons is equal to 0 because of its completely flat feature, the E doesn't depend upon K. E is independent of K, so del E del K is equal to 0, so that's why the velocity is equal to 0. If the electrons have 0 velocity, how can they be conducting? Okay, but however, a more rigorous analysis also shows the same thing. Let's talk about calculating the current. So this is the expectation value of the current operator, which is J, and which can be written as minus E and these psi and V and psi. So these psi's are the wave functions corresponding to the Landau levels. Okay, so you're taking the expectation value of the velocity operator between them, and the velocity is nothing but minus E by m psi and p psi, and now this p in presence of a magnetic field is just not the momentum, but this is equal to p plus Ea, which is what we have learned. So this has to be changed in presence of a magnetic field by P plus Ea, where A is the vector potential, and you have to take the expectation value of that. Now let's say we talk about the Jx, that is the x component of the field. That means that we are talking about vector potential which is in the x direction. So the gauge is chosen such that it's in the x direction, and these psi's, if you remember that these psi's are actually comprises of the Hermite polynomials and multiplied by the Gaussians. Okay, so and this Hermite polynomials have this property that these are written by Hn and this hn being even, it's an even polynomial of x. That's the special coordinate, and if n is odd, it's an odd polynomial of x. Okay, so which means that if you change x to minus x, for n to be even, it doesn't change sign, but if you change x to x for n equal to odd, it changes sign. So we can calculate the x component of the current, and which can be written as minus E by mLb root over pi. All these factors were written earlier, and this is equal to dy and then exponential y minus y naught square. I am taking the same gauge as I have taken earlier, and this is equal to h cross k minus EBY. So because if you remember that we have taken a gauge in which it is minus by and a 0 0, this is called as a Landau gauge. Now if you try to solve this integral, it's easy because it's over this entire minus infinity to plus infinity. This is an even function, and this is an odd function of y. Okay, so an even function and odd function, when they are multiplied, that gives you an odd function. So the integrand is odd, and when the integrand is odd, if you integrate it over minus infinity to plus infinity, this is equal to 0. Now that makes us wonder that if the conductivity of the Landau levels are 0, then how does this Hall conductivity arise, or the Hall resistivity arise, the inverse of that? And that question will be answered, but in general the the Landau levels do not have any conductivity, or they cannot conduct because of their flatness. Okay. All right, let us go to another topic which is related to this, and this topic is, let's say we want to talk about addition of spins into the problem. Okay, so we want to add spin of the electrons. As you know, these electrons intrinsically have their spins. We have not taken into account. Why haven't we taken into account? You could say this, or rather see this in this particular fashion, that since we are talking about a magnetic field which is large and pointing in the transverse direction, say z direction, which is perpendicular to the plane, then the spins of all the electrons must be pointing in the direction of the magnetic field. Okay, that's how the energy is minimized. Now if all of them are pointing in the same direction, then you don't need to talk about separately about the spin of the electrons. So that's why we didn't talk about the spin. But electrons intrinsically have spins. So what happens when we talk about that? Is there any change in the physics that we get? So let's say that we want to include spin. So one is include spin in the discussion. What happens when you include spin in presence of a magnetic field? There is a Zeeman term that emerges. Okay, and this Zeeman term can be written as, so delta, let's call it a Zeeman, so write it with a capital Z. Delta is the energy scale of the problem. So if this is G mu B into B. Okay, where B is the magnetic field, mu B is called as a Bohr magneton, and G is called as the Landau G factor, and G is almost equal to 2. Let's take it as 2, and mu B, which is the Bohr magneton, for an electron it can be written as EH cross over 2m. So this gives you 2 into EH cross by 2m into B. So this is equal to EH cross by m into B. Okay, if you take the spins into account, each spin will have this energy, extra energy, because of they'll couple to the magnetic field, and we are just simply talking about the Z component of spin. So this is because the magnetic field is in the Z direction. Okay, so it just goes by. So the Hamiltonian for such a thing is sigma dot B, where sigma are the Pauli matrices, spin half particle. We are talking about specifically about electrons, and so this gives rise to thing which is like H cross by 2 and S, Z and B and so on. Okay, that's how this thing comes. So we are pretty much talking about a classical or a semi-classical picture. So the Zeeman energy scale is, if you take this thing into account, then the energy scale is set by this EH cross by M into B. Now the funny thing is, you'll see that the distance between, or the difference between the Landau levels, okay, let's call that as delta LL, just to remind you that it's n plus half H cross omega B. So they are all equidistant. So the distance between them, I mean, distance means I'm just talking about the energy difference between them, is H cross omega B, and omega B is nothing but equal to EB over M. So this is EB over M. Okay, now this is what we have learned. So delta LL is also EH cross B over M. Okay, so delta Z and delta LL, which we have already done, they are exactly same. What it means is that, say the spectrum, the Landau level spectrum for spin up electrons will coincide with one level or one n lower of the downspin electron. So what I mean to say is that because these two are same, and this is the energy difference between the up and the downspin electrons. So suppose this is the n equal to 1 and n equal to 2, just taking two levels. So for the spin down particles, this will correspond to the same thing. So this is spin down corresponding to n equal to 1 will correspond to spin up for n equal to 2. So this is n equal to 2 and this is n equal to 1. So they'll coincide and no longer be able to call this as n equal to 1, because this is n equal to 1 for the downspin, but it's n equal to 2 for the up. And similarly, I mean, if I call this as n equal to 2 for the down, I have to call this as n equal to 3 for the up. So this one goes away. Okay, so but you see that this is a trivial, it's just that nth level of the one kind of spins, they coincide with n plus 1th level of the other kind of spins. But however, this is really back of the envelope calculation. It doesn't happen. So for example, in gallium arsenide, when these spins are taken into account, the Zeeman energy, that is delta Z, is typically 70 times smaller than the Landau level energies. So one can conclude that even though trying to include the effect of spin on this, the quantum Hall effect or the integer quantum Hall effect that we are talking about is a worthwhile exercise, however, it doesn't give you anything significant or that we should be, really worried about. It's just that nth Landau level of one spin coincides with the n plus 1th level of the other spin. 2. Let's include the electric field. Now this is important for the reason that there is indeed an electric field in the problem, which we have not talked about when we considered the Hamiltonian in presence of a perpendicular magnetic field B in the Z direction, and accordingly we have chosen vector potential to be either in the x direction or y direction, or x and y directions that we have talked about. But the important point is that we have talked about only the magnetic field and have not talked about the electric field as yet. If that needs to be taken into account, it enters through a scalar potential. Okay, just like the magnetic field enters through a vector potential, this electric field enters through a scalar potential, and the scalar function or the scalar potential that it corresponds to is Ex. Okay, the E is equal to minus grad phi. Okay, just that this relations you should keep in mind, that B equal to curl A. So there is a vector potential associated with a magnetic field, whereas the electric field is associated with a scalar potential, which we write it as phi here. So phi is equal to minus Ex. So remember, E is not the energy here. So we'll keep writing energy with a curly E. So this is energy. And this E, straight E that you see here is the electric field. Okay, so in the previous slides we of course took the liberty because there was no electric field there, but now we have to be careful. Okay, so let me write down the Hamiltonian of a system in presence of both the electric and the magnetic field, and let me introduce a little bit of change there so that you get a practice of what we are doing. Now I'll write down the gauge to be slightly different. Now I take a gauge where A is not minus By, but this is equal to 0 and a Bx and a 0. Okay, so instead of what we have taken earlier, By 0 0. Okay, now this is a valid gauge as well, because this gives you if you take a curl of that, this gives you Bz cap. Okay, and that's exactly what we want. So I take a gauge, this gauge that we just said, so this one, and that's why the y component of P is now affected, and this is equal to, so that's the Hamiltonian, and plus Ex, because of this negative sign and the negative sign of the electronic charge. So you have another this linear in X, and this change in gauge that you see is simply because I have the electric field in the X direction. There is another X here and another X here. So that's why, because otherwise you'll have both Y and X. It's not a problem at all, but it's just that I wanted to simplify the discussion here. Okay, now what I'll do is that instead of solving this again, this problem that H psi equal to E psi, instead of again solving this, there's a simpler way out. What I can do is that I can complete the square, because this is let me do a bit of so this is Py square plus E square B square X square plus 2 EBX Py and plus Ex. So you see there is a Py square, there is a term which is linear in Py, and of course these are constant terms, and if you look at it from the other way, that there is a X square and there's a X, and these are constant terms as well. So what we do is that we just complete the square and write this Hamiltonian, and then once when you do that, you are left with some things which are this. We'll take it as a little example, that this is equal to H cross omega B and minus EE. This is electric field, KLB square plus EE divided by M omega B square plus half M E square by B square. Okay, so what I do is that I entirely open it up and then try to sort of write it in terms of a complete square. So the these term which you see here, this term is an important term. This of course you have seen with only the magnetic field. Even if there is no electric field, you'll still have this. And this is a term which is, it looks like a kinetic energy, it's like a half mv square. If you can somehow relate the velocity of the particle, which is the ratio of the electric and the magnetic fields. The middle term is important because this has a k, which is the momentum vector or the wave vector. This was missing, and I said that the velocity of the electrons is 0 for the reason that the Landau levels are completely flat, which is no longer the case. It acquires a k dependence, and in which case the electrons are becoming dispersive now, and if they become dispersive, they'll acquire a velocity. And that's exactly what the idea is. Okay, and the electrons are actually displaced along the x-axis by an amount which is me over eb square. We'll see that displaced along the x-axis by me over eb square. Okay, so it depends on both the electric magnitude of the electric and the magnetic fields. So this gives you something not too difficult. It gives you a wave function, which is again a two-dimensional wave function, which is equal to your psi nk. Now I had a n anyway, because psi was a function of this quantum number n, which went with n plus half h cross omega. Now because of this new term called k, I have a psi nk as well, and it is simply it is displaced from its original by this eb square, which is what I just said, and y. Okay, so this is the new wave function, and which is different than the earlier wave function. However, the nature or the qualitative nature of the wave functions remains same. The farther the Vy, which is the y component of the velocity, is equal to 1 over h cross del E n k del k. Okay, and which now I'll just take a derivative with respect to k. As you can see that there is a k term there, so if I take a derivative with respect to k, it's simple. It just picks up a factor which is minus e into capital E into this lb square. Okay, and this is equal to nothing but e over, there's a minus sign which I should write, so this is e by h cross e lb square. And lb, just to remind you that this is the magnetic length which we have talked about earlier, which is equal to eb. So Vy, so it acquires a velocity in the y direction, and L in terms of this electric field, so it depends upon the strength of the electric field, and it also depends upon the magnetic field, inverse of the magnetic field. So it's like E by B, because LB square goes as E by B. So it's a ratio of the electric to the magnetic field. And so if you want to know that what happened to these flat Landau levels, which were earlier completely flat and of course equidistant, now let me write it, draw it with a color. So these becomes like this, it becomes like this, it becomes like this. Okay, so this is n equal to 1, n equal to 2, and n equal to 3. So E versus K, and this is K for different n's. Okay, so this is the only change that happens when you include actually an electric field. So it doesn't have too much of change or any really qualitative change, but this dispersion is important in the presence of the field. Okay, and of course if you the Vy, it, as I said, that if you put LB, this is equal to E into electric field H cross and then H cross by EB. So this is equal to E by B. Okay, so this energy that you see here, so this is the energy, not the Hamiltonian. So this is the energy that, and this is a function of Nk, and this energy is actually can be viewed as the following. So epsilon Nk consists of 3 terms. One is, of course, it's that of an oscillator. So n plus half h cross omega b is that of a harmonic oscillator, which we know, which we have seen earlier. Number 2, which is basically this is like a potential energy of a wave packet, which is localized at x equal to minus k L b square minus m e divided by e omega b square. It is potential energy of a wave packet. And third, it's the kinetic energy of a particle whose energy is given by half mvy square, which is half m into e square by b square. That's the, so if you see this, so this is the usual harmonic oscillator energy. This is like a wave packet that is localized because this is like a length. Okay, so E electric field into charge into some distance will give rise to a wave that is a potential energy of a wave packet, and this is that particle with moving in the y direction. Okay, remember that you have taken the gauge to be in the y direction, which is b into x. So this is what happens when you take into account the spin and the electric field into consideration for a charged particle. Okay, let me go and give you a physical picture of the okay. So this physical picture that emerges is that I have a this is a 2D electron gas. Okay, I have taken a rectangular sample and it is put in a strong magnetic field. Okay, let's not talk about electric field and spin anymore because we know how to deal with them. These electrons that are here, they would undergo a cyclotron motion like this, and the cyclotron radius is inversely proportional to b, which means as b increases, the cyclotron radius decreases. Okay, which can be easily understood from the classical electrodynamic equations. Okay, now this is what happens in the bulk. So the bulk is completely insulating because you see the electrons cannot drift from one side to another. Okay, or they cannot carry current in any of the directions because there are all these modes or all these electronic orbits which are closed, and closed orbits cannot give rise to such electronic transport, but we know transport occurs. There are Hall conductivity at the transverse edges of the sample. So what happens is that there are these edge modes, they cannot complete a full circle and they skip from one edge to another, which happens here as well. Okay, It happens on the other sides as well. Let us only talk about this. So you see that these actually take part in conduction, and these are called as skipping orbits. Okay, so these are skipping orbits. Now this is the skipping orbit in the other transverse direction. So actually the conduction takes place via these edge modes or the conducting modes or the conducting channels of the material. Okay, and that's why you see that the bulk of the system or the interior of the system behaves like an insulator because it doesn't conduct. So the bulk behaves like an insulator, and the edge behaves like a conductor. Okay, and they have different names. So these are of course called insulator or gapped systems where the energy level is gapped. That's why it's called insulator. And this conductor is sometimes called the metallic edge and so on. Metallic because they are conducting edge, and that's why because of this ambiguity in their behavior of the bulk and the edges, they are called as topological insulators. Okay, they are often written with TI. Okay, because the insulator, usual insulator, which are not really interesting to study because like a rubber or a plastic is an insulator. Okay, and plastic is an insulator means they do not conduct. Okay, and if you want to stop conduction, if you want a short, electrical short not to happen, then you put a spacer in between. Those fuses are made up of heavy ceramic material which are completely non-conducting or rather insulating material. They are good insulators, and there are many things in nature which are good insulators, and they are good and they are important for a variety of purposes that we see on everyday basis. But however, their electronic properties are usually not interesting. Okay, however, these ones, because they have a difference in behavior of the bulk and the edges, their behavior is interesting, and this opened up a very rich field of study, and several topological insulators are discovered. If you want to know more about them, there is a review by Zahid Hassan, MZ Hassan, in Reviews of Modern Physics. I'm not sure whether he writes with 2S, but it could be 2S. So it's again, I don't remember but if you search, you will get it. Okay, and he gives a very detailed account of the discovery and the synthesis and the properties of the topological insulators. Okay. Now, having said this, let me tell you that what physically is happening with the Hall plateaus. Okay, I take this picture, I just draw it by hand, but you have seen this picture a number of times, and I just draw two plateaus. It's understood. So this is the Hall resistivity which I'm plotting, and in unit of H over E square. And this is the rho H is actually H over nu E square, where nu is equal to 1, 2 and so on. Okay, this is what we have told several times, and I'm just showing you two new values, nu equal to 1 and nu equal to 2, and let's try to understand that what happens physically. Okay, mathematically of course we'll have to see this, but what happens physically. So let's talk about the Landau levels. Let's go to the Landau level. This is a this is completely flat, so let me try to plot it flat Landau level, and say I just talk about only 2 Landau levels, n equal to 1 and n equal to 2, or n equal to 0 and n equal to 1, either is fine, just any 2 arbitrary Landau levels. Now these Landau levels, of course, the way we have calculated, they look like 2 sharp lines with no extent, but however there is, I've told a number of times that these are disordered material, and we'll also learn that how these 2-dimensional materials are being formed experimentally, or they are being synthesized experimentally. And when you have a large disorder, what happens is that you have these levels to be broadened. Okay, each of these levels to be broadened like this. Okay, now the Landau levels are no longer sharp lines, but they are slightly broadened, and the broadened is because of the effects of disorder, which gives additional energy levels in the vicinity of this level. Just think of for a semiconductor, when you dope a semiconductor, there are n-type or p-type semiconductors. There are always additional energy levels that appear just above the valence band or just below the conduction band. So these additional energy levels will make this or rather account for this conductivity of the semiconductor, and it's exactly in the same spirit that these Landau levels, which were sharp, the degeneracy is somewhat lifted. It's not completely lifted, that is, these 2 Landau levels will never merge, n equal to 1 and n equal to 2 will never merge, and these delta LL should always be much greater than the let's call the disorder energy strength or the disorder present in the system, or the energy scale associated with disorder. Okay, so they are still well separated, excepting that they have broadened a little. And if you consider a value of the magnetic field, because you're sweeping the system as a function of the magnetic field, so when you consider another magnetic field which is larger in value than the present one, then the Landau levels will be farther separated, because the distance is given by h cross omega, which is EB over m. And as you increase the magnetic field, this will keep increasing, and so on. So what happens is that when you sweep the magnetic field, what happens? Okay, or because this is as a function of the magnetic field, so you are increasing magnetic field. So when you increase magnetic field, the density of the charge carriers or the density of the electrons increases. How it happens? Because suppose I want to understand that how in a non-interacting system, how we talk about the density. The density is given by some Fermi distribution function multiplied by the density of states, and you integrate over all E from 0 to mu. That gives you the total number of electrons or the charges that are present in the system. This is the Fermi distribution function, FD distribution, which you know from your elementary statistical mechanics, that f of epsilon is equal to exponential beta epsilon minus mu plus 1, and G epsilon is the density of states. Okay, and this will give you this n, which is the carrier density. Now, as you have magnetic field into the problem, they are still non-interacting, the energy levels change. Okay, so if you still want to calculate, your n becomes a function of B, or rather your mu becomes a function of B. That is, your chemical potential continuously have to adjust itself such that it can accommodate more and more electrons into the system as B is becoming larger and larger. Okay, so this chemical potential, as you change B, it acquires a dependence on B, and when you change magnetic field, then what happens is that the chemical potential starts rising because of the density starts rising, and it comes to the first Landau level, and it sees that there are number of conducting states. And then the conduction can happen just like metallic states. The conduction can happen without any resistance. Okay, so the resistance shows a plateau, and then it crosses the first Landau level or the lowest Landau level and goes out of it, and it finds no states that it can conduct. So there is a very large jump in the resistivity that happens till it goes to this when it starts finding a number of energy levels. So let's say we start from this and then we go to this and so on, because we are increasing magnetic field. So this is in the direction of that. So we start from here, that is when we are here. Okay, so at this point, let me point it out by, so let's say this is the point A, this is the point A, this is the point B, C and D. So this is the point B, this is the point C, and this is the point D. Okay, so D here. Okay, so as the magnetic field is increased, the chemical potential rises, and as the chemical potential rises, it enters into this Landau band. And why I'm calling it a band, because there are a number of very close by energy levels which the electron finds it easier to conduct, which means the resistivity kind of flattens, and that's what happens between A and B. So it gets a large number of conducting channels, and then it doesn't get anything from B to C, and hence the resistivity just rises, okay, and goes to a value C, and then again it finds a large number of energy levels and so on, and then the resistivity shows a plateau because it gets a lot of conducting channels and so on. So this is the origin of the plateaus in physical terms, if you like. Okay, so I think these will give you a holistic idea that how the Landau levels are connected to this whole discussion of plateaus being found at integer values of these h over e square, and how the filling, electron filling or the degeneracies are related to that. We shall be continuing from here and talk about other things which are like the experimental realization of the two-dimensional materials is one important thing, and then there are theoretical understanding or ansatz, or there are thought experiments. One of them, beautiful visualization or conceptualization of this quantum Hall effect is called as which Laughlin saw. I have written down the name of Laughlin in the first slide when I have referred to his work. He saw it as a quantum pump. So he actually talked about a disk geometry and then a flux threading through that. So there's a very nice understanding of that, which is called as a Corbino disk geometry. We'll learn that. And there are other things such as Shubnikov-de Haas oscillation. So what happens to the magneto-resistivity? Does it that is the direction, the resistivity in the direction of current. It shows oscillations as well with some particular time period or frequency. That's called as the Shubnikov-de Haas oscillations, etc. We'll see all of that.